or you can wait until the Q&A session to ask your question directly to the speakers. The title of our talk today is Open Data, Models and Tools to Support Building Decarbonization. And we have three speakers today. Dr. Tianzhen Hong is a senior scientist in the Building Technology and Urban Systems Division of Lawrence Berkeley National Lab. His research employs interdisciplinary approaches to explore technologies and human factors for planning, design, and operation of energy efficient, demand flexible, and climate resilient buildings across scales. He is an IBPSA fellow, ASHRAE fellow, and highly cited researcher. We also have Dr. Na Luo, who is a senior scientific engineering associate in the Building Technology and Urban Systems Division of LBNL. Her research focuses on building performance simulation, demand response modeling, building data curation and analytics, as well as urban microscale CFD modeling. And our third speaker is Mr. Hanley, who is a senior scientific engineering associate in Building Technology and Urban Systems Division of LBNL. His current research focuses on sensor data integration and machine learning. He is the lead developer of the Better tool for building energy benchmarking and retrofit targeting. He is a lead accredited professional. Tianzhen, you are the first speaker, so the floor is all yours.
Okay, great. Thanks, Carmel. So I want to take this opportunity to thank the IBPSA-USA's Building Data Exchange subcommittee for organizing this webinar, giving us an opportunity to share some of our research related on open data tools and use cases. And of course, we are also very interested in getting feedback from audience here. I think this is a growing topic with strong interest from many different angles. So with that, so I will the outline of the talk. So I'll talk just a few things about the background. We're going to talk about three ontology and schemas we developed, and then go to some related efforts about developing the open data sets, and illustrates some three use cases about using data-driven approaches, how to produce insights and inform decision making. And then we will have the Q&As. So I think the background, right, is these four sort of figures or images illustrate. First is the climate is changing, and I think everybody, right, agree with this. As we see, it's not just the long-term warming of the climate, but it's also the more extreme weather events, right? We're not talking about heat waves getting more often, getting longer, getting hotter. Right, we're also talking about, for example, last February, we had the winter, right, a snowstorm in Texas. And traditionally, the heat is challenging in that area, but the winter, it can a new challenge. And of course, the figure on the top right, that shows our buildings are also changing, right? Building used to be, a very simple, pure energy consumer. Take electricity or natural gas from the grid. But now we may have on-site energy generation from PV. We may have electric vehicle. It can be, bi-directional. Means you can charge, but also during some special time, you can also use the battery of the EV to provide energy back to the building, right? And on top of that, you also may have some other type of energy storage, electric batteries, thermal energy storage. So it becomes quite interesting, but also complicated as a bi-directional, energy user. And all these then leads to, right, the changing net energy demand on the grid. I think as the bottom right figure shows, that's the California state's net electricity demand. And you can see, right, the curve is, we call it a dark curve, but basically it shows that during middle of the day, because of a lot of the renewable energy produced from PV, so basically the net demand is pushed down to the very low level, and which actually may have to curtail some of the renewable generation from PV or wind turbine, because some of those based on electricity generation is from hydro, from nuclear, and those are not easily to modulate, to shut down, and so all these landscape changing basically also requires our building, our energy demand need to change, need to adjust accordingly. And of course the peak demand, right, is changing from the early afternoon to now is we're talking about 4 to 9 p.m. and that's where the energy is more expensive, right, because of the sunsets and traditional energy sources have to come into play. And the figure on the bottom left basically that just shows the common intensity across the 87, 60 hours of the power grid. So as you can see, the power is much cleaner during the the daytime of summer, and it gets dirtier when we are getting to the evening time or the winter time. So all this just implies, some of the technology policies we have to think about when we try to decarbonize our buildings. And so as the 4 blocks showed here, I think from our perspective, the building decarbonization basically touch upon these 4 pillars. And of course, right, efficiency. So that's the technology, we are all very familiar with, use the energy efficiency technology to reduce the amount of energy needed to provide certain levels of services, right? And flexibility, as we just talked about, because of the common intensity and also the pricing of electricity, vary, right, with the time of the day of the year. So we want to make our energy demand flexible. When energy is clean, we can then, consume more or maybe store energy, right? And then use less when, energy is it's expensive or when it's more, common, intensive. And resiliency, so that's the angle we need to think about when we transit our building stock, right, for zero carbon, and we need to make our buildings more resilient because of the more frequent extreme weather events. And you may have coincident power outages, right? So that would results in excess indoor temperature, very high or very low, and that can cause real health risk to occupants. So then, of course, very important is to think about the elephant in the room of this building decarbonization, which is the sufficiency concept. And this is very important, but it's usually not talked about too much. And thinking about, right, if we can, as humans, right, try to, adjust our needs. For example, if we can live in a smaller space, smaller house, but the space is more flexible for reconfiguration, right? If we can rely on adjusting some of our closing levels to enable a wider comfort temperature, that would provides lots of potential for reduce the heating and cooling needs from our HVAC systems. So things like that, I think that provides quite some opportunity. And that's why we believe the sufficiency is a very important pillar of this overall, building decarbonization. So we did a review about 2 years ago, looking at as we have more and more data, different type of data from different sources, right? It provides some potential to unlock the value of the data using techniques like AI and machine learning. And so I'm obviously this is a very hot topic, right? And I think the figure just I borrowed a figure, but it shows that machine learning technique can be a very, very powerful tool for our buildings industry. When you think about how we address the decarbonization, the energy, flexibility and resiliency. So basically the review, if you're interested, I think it's published as a journal article at the journal Energy and Buildings, but we review how machine learning techniques have been applied across the building life cycle, from the design to construction, commissioning, operation, maintenance to control and retrofit. And you can see there's more and more, right, these kind of studies get published at different type of journals. And obviously it's a lot of focus on operation maintenance and control, but it's a huge gap in using machine learning techniques for building commissioning, for example. So those are maybe the area that would have more opportunity. We are also looking at what kind of machine learning algorithms, right, were used in different applications. For example, in building design, in building controls, as listed in the table. So I will pass this to my colleague Nalo to talk about a data tools review we did about 2 or 3 years ago.
Yeah, thanks, Tianzhen. So data tools play a very big role when you try to store the data and especially curating the raw data into the research-ready data. So to get a better understand, we categorize the data tools into 3 major groups as shown in the left. So the data terminology and data dictionaries at the very bottom layer are the fundamental for standardizing the terms. And the data ontologies and schemas on the second layer basically utilize these forms of dictionaries to define ways of organizing related data items and denoting their relationships. And finally, data platforms at the very top layer are used for storing and managing large amount of data organized in a uniform way using a specific data schema or ontology. So then based on a survey within the data experts in 4 national labs, so we compiled a list of 24 building data tools covering different phases of the building life cycle and different applications. So we grouped these 24 data tools into the 3 categorizations as shown on the right. Next slide, please. So we also compile a lookup table of the key features for these 24 data tools, including the tool category I just mentioned and data coverage, data relations, flexibility and extensibility, stage of application during the building life cycle, as well as the adoption status. So the information in this lookup table can facilitate users to choose the appropriate data tools from various candidates for their specific use cases. So as the review results, we found that each data tool is capable of representing just a portion of the building data, but the tools that can represent the occupant data and design basis data are still limited. So we probably need a combination of these data tools when sharing and curating the building data sets, or some efforts are needed to enhance a certain data tool to fill this gap. So this motivated us to enhance the current brick schema for representing the occupant data, which I will talk about it later. So I won't dive into the details of this lookup table because of the time, but feel free to check it out in a published journal paper showing on the left if you have interest. Next slide, please. So this review efforts also highlighted some representative and popular data tools from each category. So we identified the unique features and limitations for each tool. And the takeaway conclusions are listed in this table. So to summarize, I think we think a general gap for all the data terminology tool is that we need to supplement new terms for occupancy and occupant activities, indoor and outdoor environmental data, sensors and meters, as well as data for evaluating the demand flexibility. And then for data ontologies and data schemas, one gap is the coverage of all building data types. And the other gap is the lack of standardization in the current metadata representation. So for the data platforms, data privacy and security issues are still the major challenges so far. So in the next couple of slides, I will focus on how we enhance the current brick schema to represent the occupant-related data points. So BRIC was developed by a group of universities to standardize the semantic description of the physical, logical, and virtual assets in buildings and the relationships between them. So entities in buildings are represented as nodes in the BRIC model, and each entity is an instance of a certain class and can have relationships with others. So currently, there are 3 key classes included in the BRIC schema, which are equipment, location, and point. And they will have some relationship between each other. Yeah, so next slide, please. Thank you. So we summarize the main typology of the occupant data as shown in this table to see what kinds of occupant, excuse me, what kind of occupant-related data measurements are available and needed to be represented in this enhancement. So basically, we group the occupant data into 3 categories. The first one is occupancy, which includes the occupant presence status, occupant count, and occupant location. And the second one is occupant action or occupant behavior, including like the adjustment to the thermostat, window, door, blind, lighting, and other personal devices. And the third category is, we call it occupant demographic and contextual information, including the attributes such as occupant's gender, age, and country, etc., and the attitudes such as the occupant comfort, preference, and energy use styles, as well as other occupant proxy parameters such as Wi-Fi access points, numbers, and CO2 concentrations. Yeah, so in the next slides, we propose an extension plan to the current break schema, trying to represent all this occupant data I just mentioned in the last slides. And also, we want to build the relationship of this occupant data with the existing building and its subsystems. So the right plot shows the overall extension plan in 4 aspects. The first one is we will add a new class called occupant in parallel with the existing equipment location point. And this class describes the occupant demographic and contextual information, such as the gender, age, and thermal preference. Something. And secondly, we add some new subclasses under the current equipment class, such as the envelope system, window door, and personal thermal comfort devices, such as the personal like ceiling fan or some other things. And thirdly, we also add some new subclasses under the current point class, such as the window door status and window sensors, which is right now is not available in the current break schema. And last but not least, we add a new class called a device property to represent the occupant's controllability on the equipment. And this includes 3 subclasses. The first one is to represent the degree of control, like whether the devices are binary control, continuous, or stage control, or is not available to control at all. And the second subclass is called level of occupant accessibility, which is used to represent how accessible a device is to be controlled by occupants, like it's shared or just can control by one occupant. And then the third subclass is called mode of control, which is to describe the policy and the algorithms under like which the device is controlled, such as like manually, automatically, or dynamically responds to the grid signal. So this is the overall break schema extension plan, and we have implemented this extension to the current break schema and generated a demo version, excuse me, of the updated schema for further testing. So the GitHub link is shown on the left, and in the next slides, you can see that we collected 68 occupant data sets from the ASHRAE Global Occupant Database project, and then we compare how much of the data points could be represented using the original version via the updated version of the break schema. So generally, after using the extended break schema, we can cover 23% more data points, which is a big enhancement. In the next slides, we also tested the extended schema in using a Building 59 data set. So Building 59 is a media-sized office building located in LBNL campus. So this data set contains like more than 300 data points covering like the energy use data, outdoor, indoor environmental data, HVAC operational data, and the occupant data. So the results shows that the extended break schema can capture more more occupant-related data points, and makes the model more comprehensive. Yeah, so next slide. Yeah, so I think, Tianzhen, I can give this back to you and Han.
Okay, yeah, thank you, Na. So I can continue from here. So as Tianzhen mentioned earlier, energy flexibility of buildings can be an important resource for a sustainable and reliable power grid, because we can change our operation to avoid energy consumption during the peak hours or carbon intensive hours. So although there are a lot of attentions from industry and research community on the energy flexibility, there's still a lack of commonly agreed definitions and categorizations, and also the methods to quantify energy flexibility. And as Na mentioned earlier, ontologies are powerful tools for knowledge sharing and standardize the definitions and relationships between the concepts. So we reviewed some existing ontologies related to building energy. As you can see in the figure on the right, those ontologies focus on different domains and subdomains. Some of them focus on assets topology, some of them focus on modeling and analysis, some of them focus on smart building. However, there's still a lack of ontology dedicated to building energy flexibility. And the gaps include how can we describe the energy flexibility technologies and resources in buildings? How do we describe the flexible operations? How do we model them? And how do we quantify the flexibility using the measurements or simulation data? So that's motivated us to develop this energy flexibility ontology. So Tianzhen, next slide, please. Yeah, this slide just shows the major component of our ontology. So you can see basically there are 6 major parts. The first part is application scopes. So this will define what are the scope of the application. Is it at system level, building level, or even community or district level? And what are the performance goals? Is it to reduce energy, to reduce cost, or peak demands, or carbon emissions? And building services will describe what kind of flexible operations will have the impact on which kind of building services, including the thermal comfort, the air quality, and maybe other services. And the next component is the flexibility resources. Basically, what are the technologies that can enable the flexible operations, and how can we categorize them? And we also describe the flexible load characteristics. So basically, we describe, how does the flexible load profile look like? When is the flexible operation start and end time step? And what's the maximum peak reduction and stuff like that? And finally, we also include the energy flexibility key performance indicators. So we reviewed what kind of KPIs are available and what performance aspect they indicate, and what kind of data we need to calculate them, and who might be interested in those KPIs. So the ontology is open source on GitHub. Sorry, I didn't put the link here, but if you're interested in, you can reach out to us to get the link. Next slide, please. Yeah. So this picture just shows example of how this ontology can help to standardize the categorization of the flexibility resources. So as Na introduced earlier, the ontology has different classes. You can have subclasses and instances. So in this figure, the rectangles with the yellow dot are the classes. So if we look at the central part, the class with the green outline, it's flexibility resources, and it has multiple subclasses. For example, the distributed energy resources on the left, and subsequently they have even more subclasses. And at the outermost, those rectangles with the purple dots are instances, or the flexibility measures, if you will. So yeah, this is just standardized, how we can categorize the flexibility and how we define them. Next slide, please. Yeah, this is another example to explain how this ontology can semantically describe the key performance indicators for to quantify the performance. So as you can see, we have over 20 KPIs, and we use the flexibility factor as an example. So it has 3 performance goals. It is usually used to identify whether we reduce cost or emission or the grid energy consumption during the flexible operation. And it might be interesting to researchers and building operators. And to calculate it, we have this formula which requires 3 kinds of input, including the load profile, the event start and time. So with this ontology, you can see we can really define this formally and also specify the data requirements and measurement requirements. Next slide, please. Yeah, so the ontology is just a tool. It's not an application, but it's knowledge base. So it can support other higher level applications. So this slide shows 3 potential use cases. First one is it can support energy flexibility quantification using modeling and simulation. So for example, if we combine the E-font with Energy Plus IDD, we can map, okay, which kind of system or equipment in Energy Plus can support which kind of flexible operation. And this can really help the energy modelers to quickly identify the resources in their model and run simulation to calculate the flexibility potentials. And similarly, we can combine our ontology with other data schema or ontologies such as BRIC, so that we can retrieve the data required to quantify the flexibility from the building automation system and maybe from other sources. And finally, we can also use this ontology to help configure the controllers and guide the design of the control objective functions to optimize the building energy flexibility. Yeah, so Tianzhen, I think that's about the E-font.
Thanks, Han. So another tool, related to data schema is the suite of tools we develop to model and simulate occupant behavior in buildings. And I think so. This just shows a list. There's the ontology. We call it DNA's framework, and then we build XML schema, OBXML, built on top of the the DNA's framework, and we also develop some tools to facilitate the use of those schema, like OBFMU is a functional mockup unit, so it can be used to simulate occupant behavior in the co-simulation mode with other building energy modeling tools like Energy Plus, ESPR, IDAIs, And we also developed some an occupancy simulator, which take the description of the occupant behavior and their movement, and then use the Markov chain to simulate their movement, between spaces in the building, so that it will generate stochastic occupant schedules in a very detailed way for every space. And there's also a Modelica, like a building occupant package. And so that's, for folks that use the Modelica, based tools that, also provides an opportunity. And, there's Open Studio Occupant Availability Gym, which, sort of captures some of the tools we talk about, but, make them available as an, occupant, as an Open Studio major. Yeah, and I think earlier now also talk about a brief schema. So I think these are the suite of tools that provides modelers, engineers, an opportunity to use these together with your building energy simulation, try to capture the impact of occupants. And depends on what kind of building, what kind of projects working on. Sometimes those influences are significant, and you want to understand and try to compare your design operation strategies, right? Considering all different metrics, but also very important is the human building interaction. So I don't want to get into details, but so these are all published work. Basically we use this XML schema to represent occupants' behavior. For example, in this DNA's framework, the needs may be represent your thermal comfort, acoustic, indoor air quality needs, and the drivers are basically represent the key variables right? For example, thermal comfort, and you have temperature, humidity, you have some other variables, and like air velocity, your tracing label activity. And then it's action. Action means if you feel uncomfort or you want to adjust something, right? And so, what are the actions? You can open, close window, you can adjust thermostat, you can, add or reduce your closing levels, right? And the system basically it's all the things, devices, envelope components that you can interact. It can be a window, it can be a door, it can be a thermostat, it can be, a personal fan or devices that you can adjust, to meet your comfort and needs. So next we get to these data set development work, and I'll pass it back to my colleague, Yana.
Yeah, thanks, Tianzhen. So I will talk about how we develop high-resolution, well-curated data sets based on the FAIR principles. So the FAIR here is short for findability, accessibility, interoperability, and reusability. So the website showing here is a project data portal, which is hosting all the data sets that I will introduce later. So feel free to check it out after a very simple registration. Next slide, please. Yeah, so to achieve the FAIR goal, we propose a data curation workflow, which shows in the very middle of this figure, which contains three major steps. The first one is data cleaning, which is to do some quality check, such as reducing the missing rate, outlier rates. And the second step is data standardization, including generating the metadata of the data sets, sensors, and meters. And the final step is to upload the data to a data portal, which allows end users to browse, query, and download both the raw data and the research-ready data. So the project team developed 4 tools to facilitate this data curation workflow, trying to make the workflow more automatic and user-friendly. The first one, we, as shown on the left bottom, we develop a data pipeline to digest and customize the raw data, and then to conduct the quality check and to fill in the missing data using multiple imputation algorithms. So this is what data pipeline is work for. And secondly, to as shown on the right bottom, to facilitate the data standardization process, we propose a metadata JSON schema to represent the metadata of the dataset, which can provide the high-level contextual information of the dataset and to illustrate the application perspectives. This figure probably too small, but basically we covered 4 aspects and covered different types of the data points. Yeah, so the third one, we also attach a break model for each research-ready data set, as shown on the top right, basically to illustrate the metadata of sensors and meters. So as I just mentioned, we extended the break schema to represent occupancy and occupant behavior related data points. And another related effort is we also develop a GUI-based semi-automatic tool called WithBreak to expedite the break model creation process. So people have fewer like programming experience or have like little knowledge of the break schema can also like get in touch and create a break model for their data sets. And lastly, on the top left, the project developed the building benchmark data set BBD data portal to store, catalog, and standardize, preserve, and then publish the building data sets. So to achieve the FAIR goal, this platform was designed scalable and easy to maintain and easy for users to browse and explore their desired data sets. So next slide, please. So following the data curation workflow I just showed, the project team has developed already curated 12 datasets covering multiple building types, different climate zones, and can support and can support various use cases to understand and optimize the building energy efficiency performance. So I won't dive into these 12 data sets, but as I mentioned, if you have interest to know either of them, just check out the data portal I just mentioned. Yeah, so I will give it back to Tianzhen to talk about the ASHRAE global occupancy behavior database.
Yeah, thanks, Nat. So just to give credit, so the project not just talk about, it's a joint effort between LBNL and 3 other labs, PNL, Unreal, and Oak Ridge. So these are 12 data set. Actually, the team spent quite some effort, and it's good quality with lots of metadata models and descriptions. So I think you may want to take a look whether you can find some use case. So I'm going to move on. I think so. This is the ASHRAE Global Occupant Behavior Database. So it's a joint effort with Syracuse University. So Bindong, it's the PI and that university, and the project is sponsored by ASHRAE, but also co-sponsored by BTO. And so one of the questions is, well, we have those occupant modeling tools, but we really need to get data. Yeah, and these are data from different building types, from different countries, different cultures. So we can develop those different behavior models that are appropriate, to some of your buildings or your projects. So that's the goal. And these are basically we collected and processed the 34 data sets, and this is a contribution from 15 countries. And now it's already published at the data portal shown on the top. And we believe this will be a continuous effort. We would like to get many more. This is just a starting point, but we definitely interested in getting a 2.0, through ASHRAE. So Han, do you want to talk about this data set?
Yeah, sure, Tianzhen, thanks. So we also developed a synthetic building operational performance data set using simulation, and this is an open access data set. And we use Energy Plus and DOE prototypical building models. So this is a detailed version of the models. And we consider 3 locations, including Miami, San Francisco, and Chicago, and 3 efficiency levels, and also 30 historical weather data, 30 AMOYs, and also 1 TMOY3. And as you can see on the top right, we instead of using the static occupancy schedules, we use the stochastic occupancy schedules and also lighting and mail schedules. And we consider 5 different scenarios for each of those combinations. And in total, we generated close to 1,400 simulations. And the data set is in HDFFI format, and you can access it using AWS. And we also prepare the brick model, so you can check, what are the system configurations. And this data set has been used by researchers to for example, benchmark their energy consumptions, to test their load profiles, clustering algorithms, and also pre-training the controllers using data-driven methods. So back to you, Tianzhen. Okay, so I'm looking at the time. I think we need to speed it up. That covers the 3 use cases. So I think the first example is looking at the EcoV data set and think about how those kind of data set can provide value. And this example is interested in looking at the smart thermostat data and how we use it to inform the safe power outage. And these are utilities, right? Sometimes they may have to do rotating power outage during the extreme heat weather, because the peak electricity demand may be more than what they can deliver. Right. And so in those kind of situations, then the question is, where are the communities that you do this rotating power outage, and how long you can do it to ensure that the indoor overheating does not cause these huge risk to occupants. So the question is, can we use those kind of smart thermostat to answer this particular question?
So EcoV data set, I think a lot of you know, but it's getting to be a very nice resource. Currently, it has about 200,000 thermostats, mostly about 80% in the US and the others are in Canada. So this is a very nice data set. It's every 5 minutes, and it's got details about indoor-outdoor climate, climate parameters, but also the runtime of the fan, compressors, and HVAC equipment. But what it does not have is the energy use of the fan and compressor. So that's sort of a limitation. So what we are interested in is using these data, right? We try to understand the thermodynamic of a house. And this means, right, how long does the indoor temperature change, with certain outdoor temperature, during the power outage, then you don't have any heating or cooling, right? So we use this simplify, first order equation to approximate the dynamic energy balance of the house, and then use the EcoB data set of, to try to calculate these time thermal constant. Right, and of course we have to find a spatial period when some of the unknown items, doesn't matter. For example, we'll try to find a period that HVAC system is off, means the house is in free floating mode, and also find the data, during the nighttime, means the solar influence is minimal. So, after all this technique, we are able to, calculate the thermal constant for, all the buildings in the US. And this just shows the distribution of thermal constant across the, the 48 states in the US, but also a few provinces, in Canada. And as you can see, obviously the newer built house, they have a much better thermal constant because of much higher energy efficiency, better insulation, and less, air, infiltration. And then we use this, right, try to simulate when it's a heat wave and power outage, how long does the indoor temperature, right, rise from the comfort set point, for example, 24 degrees Celsius, to a level that people will start feeling hot or feeling not comfortable. And it can be, 28 degrees Celsius, maybe for healthy population. And, or even to the next level, 32 degrees Celsius, then people start to, experience some, heat hazards. So basically the result shows that most of the house, right, has this thermal constant about 1.5 to 2.5 hours. That indoor temperature range from 24 degrees Celsius to 28 degrees Celsius. But if we have a advanced notification, basically people can do some pre-cooling or deep cooling. Instead of cooling to 24 degrees Celsius, you can cooling it to 22 degrees Celsius. And this deep cooling can buy you another hour or two. Is a safety in terms of to mitigate the indoor overheating risk. So that's a quick one, and the next one I pass to Han to talk about the second case study.
Okay, thank you, Tianzhen. So in the first case, Tianzhen talked about using the RC model to infer the thermodynamics. So in the second case study, we're interested in using machine learning methods and also investigate how transferable those models are to different building types. So we're still using the EcoB data set. So this figure shows overall workflow, which includes data preprocessing, deep learning model training, and transfer learning. So I won't go to the detail here, but I will show in the next slides. So for data preprocessing, as you can see, there are different building types, and we sampled 3 building types: the single detached homes, a townhouse, and also apartments. And we chose the data from 3 US states, including California, Texas, and New York. And there are 2 system configurations, with and without electric auxiliary heating. And after we sampled the data while keeping the metadata distribution, we did some processing, including extracting the data from only the pre-pandemic data periods for fair comparison, and also filling the missing values and adding the outdoor weather data that we obtained from NOAA, and also divide this data set into seasonal chunks. So when we train our model, we can retain those seasonal patterns. And on the final step, we split the data into the training, validation, and testing set. And we packaged all those pre-processing into the Python and PyTorch routines. And next slide, please, Tianzhen. Yeah, so this slide briefly talk about the model architectures we used. So here we compare two model architectures. The first one is using the simple long short-term memory model. And on top of that, we also added a 1D convolutional layer for feature extraction. And for the multi-horizon prediction, we use a fully connected layer. And the table on the right shows the hyperparameter tuning options. You can see we tune the learning rates, the hyperparameters for the CNN and LSTM layers, and the right column shows the final values that we choose to train our models. Next slide, please. Yeah, so here's the result that we compared, the model performance between the vanilla LSTM and the CNN LSTM architecture. So basically, we tested our models on 164 residential buildings, and you can see the CNN LSTM model architecture achieved slightly better performance than the vanilla LSTM model, and also you can see the standard deviation of the prediction error is lower in the CNN LSTM model architecture, which means it's more robust. Next slide, please. And in addition to the deep learning, we also apply transfer learning to investigate, how transferable those models are to, similar but different models of different buildings. And so basically, we selected, the source buildings from the 164 pool, and then we retrained it or tuned those models with the target building datasets, which is a different set of 73 buildings. And we compared 4 different transfer learning strategies, and we found that freezing LSTM actually performs the best among those different options. And in the next slides, we also compared, how different locations, building types, and also the system configurations influence the transfer learning performance. And you can see for most of the cases, the transfer learning could improve the model accuracy. So the dots above the dashed lines in the 3 subplots shows the, the models with the improvement. And there are only a very few homes that the performance actually reduced. Next slide, please. So some of the applications for those deep learning models includes, we can do a heat resilience analysis at the single building or community scales. And also we can do occupant-centric thermal environment assessment because we can predict future temperatures of the homes. And it can also serve as surrogate models for MPCs or reinforcement learning based optimal building controls. Back to you, Tianzhen.
Yeah, now talk about the last one.
Sure. So the third case study shows how we utilize mature data sets to do some energy and occupancy analysis, especially focusing on the performance before and during the pandemic. So we were using the Building 59 data that I just briefly introduced, and more details about this 3-year data set could be found in a recent published paper published in the Scientific Data. So you can check it out on the top right. So next slide, please. So first, we look at the electricity consumption at the whole building level and 3 major end uses. So we found the electricity is normally consumed higher in summer than in winter. And when comparing across the years, we found the electricity use in 2018 is higher than that in 2019 and 2020, which is due to the energy retrofits for improving the building efficiency in 2019. And another conclusion is that there is no significant electricity reduction during the pandemic. So when looking at a more granular level on the right, so we can see that the HVAC operations normally consume 10 times more electricity than lighting and mouse in this plug loads in this building before the pandemic. And well, during the pandemic, there was a 50% to 85% of energy use reduction happening for lighting and plug loads, but which is very, very big. But for HVAC, there was no significant reduction at all. So to investigate why HVAC still consumes so much energy when the building was only partially occupied during the pandemic, so in the next slides, we compared the supply airflow rates before and during the pandemic. So the orange line is the year of 2020, and the green line represents the year of 2018. So the supply airflow rate rapidly increased at the beginning of the pandemic and remained higher than the same time in 2018 until the end of October. So we think this change of control is to address the higher requirement of ventilation and indoor air quality during the pandemic. But this will definitely induce a very high demand of HVAC, especially when the outdoor fresh air in Berkeley area is very cool to warm up. So in the next slides, we select a typical summer day on August 5th, 2019, and a typical winter day on January 23rd, 2020, to analyze the load shape before the pandemic. So we can see in summer, the HVAC demand jumps around 10 a.m. and remains high until 6 p.m. But in winter, the HVAC demand basically remains at a relative flat level. And for plug loads and lighting, the demand patterns are similar across summer and winter seasons, which are both at a higher level when the building is started to be occupied during the daytime. So in the next slides, we also generate the load shape of a typical summer day during the pandemic, as shown on the right, and compare it with it before the pandemic. Next slide, please. Yeah, so we can see an obvious conclusion is that lighting and plug loads consume much less electricity during the pandemic, since occupants were mostly working remotely. But we can see the HVAC operation actually consume more electricity, both for day and night time, which, as we already assumed earlier, is because of the higher requirements of the ventilation, as well as the cool outdoor fresh air in California. And lastly, in the next slides, we show the relationship between energy use and occupant count. So we generated a scatter plot of the occupant count with the whole building level electricity use, and using the average data collected from May to July in 2018 before the pandemic. So the 24 circles represent the 24 hours within a day, where brighter dots represent daytime and darker dots represent nighttime. So the size of the circle represents the scale of HVAC use from 40 kilowatt hour to larger than 60 kilowatt hour. So this plot clearly showed that the occupant count has a positive impact on the electricity use, where a large amount of occupants will yield a higher electricity use, both at the whole building level and the HVAC end uses. Yeah, so Tianzhen, I'll give it back to you for summary.
Okay, the last slide. And so as we illustrate by some of the data tool schemas, ontology, data set, and some use cases as examples, how data analytic, right, can be used to provide values to inform building design operation. So I think the opportunity, obviously, we're getting more data, right? Big data depends on how we define the big, but definitely we're seeing, right, more and more data becomes available, to the public. And advanced computing, I think, right, we all know GPU stuff and getting, right, more powerful, but also getting more affordable allows most people to do this kind of, data analytic and modeling. And also the, there's advancements in machine learning algorithms. And I think that's also something very exciting, how we think about using those in our buildings, research. I would mention, we are, basically this is my personal opinion, we are at a very, very early stage of this concept of digital twin of buildings. And definitely thinking about the data, the computing, the algorithm, those are the good, blocks to help us build these kind of, data-driven digital twins, in the future. Of course, challenges still remain. I think curating data is, based on our experience, still very tedious and expensive process, and especially developing those metadata models to facilitate semi-automatic analysis and modeling. And yeah, and industry adoption. I think, right, at the end of the day, it's a value proposition, right? How industry see the value, want to spend efforts and investments, in all the data-driven, techniques and applications. So thank you very much. I want to stop here. I think we're over time a little bit, but hope we still have some time for Q&A.
Excellent. Thanks, Tianzhen and Han, for your very interesting presentation. So we'll open it up for questions. I see a couple. This is more of a comment from Heidi Van Eden. She indicated that she was researching a paper on the role of the quantity surveyor prioritizing decarbonization in building for the New Zealand building industry to present at PAX next year. And basically, she finds it very interesting that to see what other countries are doing. So she probably I think she put her email in the chat, so possibility there to follow up with her.
Okay.
I also see I think I saw a hand up, not anymore now. Anyone else has a question? I see one. Yeah, go ahead, Quing Yao.
Hi, good afternoon. Could you hear me?
Yes, we can. Yeah.
Yeah. May I ask one question? So first, thanks very much for this wonderful presentation. So I can see that you have done extensive work on building data standardizations, and you have a lot of applications for building management optimizations. But in reality, most of the buildings, especially for residential buildings, they don't have equipped with the sensors. Like in your buildings, you have loads of sensors to record the data. So my question is, how could your research outcomes be applied in those kind of buildings which have very limited buildings, limited data? Thank you.
Yeah, a very good question. Yes, and definitely, right, when you talk about different type of buildings, different buildings, they have, right, different levels of sensing, metering, and also, right, depends on whether they archive the data. Based on our previous experience, a lot of the commercial buildings archive data only for a month or two, and then overwrite the data, which basically, right, lose the, significant value of the data. And I think a technique we have been trying to explore is Han talk about this transfer learning. So definitely we have some buildings, similar to building type or your location, those buildings may have more data. You can use those kind of data to train some sort of machine learning models, and then you can transfer the model, right, to some specific building you are interested. Those buildings may have limited data. So basically you retrain the model, adjust the model, and then use that as a starting point for your research. So that is one technique we see that may help address some of the data gaps.
Yeah. Thank you. So I'm not sure if I could ask another question.
Yeah, go ahead.
Yeah. For I think in Lee's his research, he used LSTM to predict the thermal indoor thermal indoor temperature. So get a very high accuracy. And then in this lady's presentation, we know that actually the occupant behavior account for have a huge impact on the energy consumptions, make a great discrepancy. So I want to know if he's because since his prediction is very accurate, so I'm not sure if he has taken the occupant behavior into consideration, and because apparently we can see the prediction accuracy is very, very high.
Yeah, that's a good question, Qingyao. I think in our input, data input, we have the occupancy status that's recorded by the ecobee thermostat. So our model can actually, use that information to predict the temperature. And another point is, in the conditioned space, when the temperature is controlled, actually the temperature trend is pretty predictable. Regardless of whether there's a lot of occupancy activities.
Okay.
Yeah.
Thank you very much. Thank you.
Yeah, sure.
Questions. I see another hand up there from Mohammed. Mohammed, go ahead.
Sorry, can you hear me?
Yes, we can. Yeah, go ahead.
First of all, I very much appreciate for your great presentation regarding to machine learning techniques in the building energy simulation. I have a question regarding to your experience of using machine learning techniques. If I'm right, you have used both neural networks, conventional neural networks, and reinforced learning. My question is that according to your benchmarks, which one have yielded actually the best results? I mean that neural networks or reinforced learning.
Yeah, a good question. I think Han, yeah, you want to take this?
Yeah, sure. Yeah. So for the thermodynamics prediction, we use two different neural networks. The first one is with the LSTM only, and the second one is we combine convolutional neural network with the LSTM. So we use the CNN to extract the features, but still use LSTM to do the sequence modeling. And we didn't use our RL for the prediction because RL is for sequential decision making, so it's usually used for building controls.
Okay, and you have used only one R1C actually reduce order model, right?
Yeah, so in the first case study, I think we only use one R1C model.
Have you tried, for example, 3R2C? Because I have come to, for example, some articles using of 2 resistance or 3 resistance, 2 capacitor, something like that. Have you tried with other reduced order models?
We haven't. So Tianzhen, please correct me if I'm wrong. So because the ecobee dataset only has like one thermostat in the entire home. Maybe some homes have multiple thermostats, but we don't have the temperature, for example, from the envelope and other locations. So we don't have enough data to train the 3R2C model. But
okay.
Those can be very interesting.
Anyway, thank you for your responses.
Yeah, you're welcome.
Yeah, good question. I think in general, that depends on what kind of application, right, you're talking about and what kind of data you have. You probably need different type of machine learning algorithms or models. I think that's not like a perfect algorithm that work, right, for different type of, problems. So Kamel, I think there's a few questions in the Q&A list.
Let's see. Oh, yeah, yes, I see there are a few, 3 questions. So the first one is, have you considered applying your machine learning capability and techniques to energy storage technology, especially thermal energy storage on buildings?
Yeah, a very good question. I think you probably know about Professor Jordan Nagy, right? The major developer of this CityLearn, right? And I think that's a multi-agent reinforcement learning platform. I think that they are doing a study basically looking at a community level, how these different type of distributed energy resources, including, energy storage, that can help, enable the energy flexibility. So I think that's ongoing research there. And I believe we have a research and basically a journal paper under review, and that is particularly looking at how we control a chiller plant with energy storage, like when to charge, when to discharge, and depends on the pricing signal from the grid. So that's also using some of the transfer learning, technique. And I believe some other researchers are also actively working in these topics. So there will be more studies, available.
Okay, another comment here that says the results are somewhat counterintuitive. There may be some reason. I'm not sure.
Yeah, I think this is probably a response to my earlier response to Yimin. So basically, he suggested us to take a deeper look at the HVAC operational data to explain the results. But what we presented is just a preliminary analysis, just focus on the supply air flow rate. Yeah, I think that's the response for that. Yeah.
Okay, and the next one is says, I'm wondering how we can also combine embodied carbon impacts and integration of more stringent building energy standards.
Very interesting point. I think that's a very big question, and I'm sure the research and community and the building industry now it's also quite interested in embodied carbon. As we are doing very energy efficient building operation and control, so the operational energy use and carbon emission goes down in the future can be significantly, but the material, the construction, practices, I think those has a huge impact on, life cycle carbon emission. So that's, a lot of research ongoing, and it's also more emerging tools available to help you sort of, do the life cycle, carbon accounting. And obviously that also relates to the building energy code, and ASHRAE actually is developing this building decarbonization roadmap. It's also a guideline, I believe. Yeah.
Okay. Any other? We'll take maybe one more. I see a comment there. Thanks for the amazing presentation. For applying ML in prediction, we can see promising in prediction accuracy. When it comes to reality, it is usually not the case, which makes me quite doubt the reality of ML. So comment there. One question from me, based on your literature survey, there are so many schemas out there, and can you comment on the maintainability of those schemas over time, if you gathered any information on that? Mm-hmm. And do you see some level of convergence somehow, where more and more people are using the same schemas, or do you see it very difficult for convergence to occur, and we may have many schemas indefinitely? Mm-hmm. I was wondering if you could comment on that.
Yeah, Kamel, definitely. I think, and this is the critical role I think this IBPSA-USA BDE, subcommittee can play, to help develop some standards, based on a consensus. I see it's a positive trend. People are not looking to reinvent the wheel. They're thinking about developing tools based on existing tools ecosystem. An example, for example, the brick schema extension, we work with the brick, community to implement some of those extensions, to facilitate particular, use cases and applications. And, for example, some of the occupant modeling, we are also, through ASHRAE ongoing project, we try to look at how some of those metadata can be represented, expanded as part of the building information modeling. So I think there's positive moments that people thinking about leveraging the existing, those more industry recognized tools instead of, developing something, from scratch.
Okay, that sounds good. I think I don't see any more questions, and I think we've addressed. I can say we'll take one more from this last question. Go ahead, Mohammed.
I'm sorry for disturbing you once again, because I'm new in this field actually, and I have read some articles because as I understood from your presentation, you have focused only on black box methods. That means data-driven methods. But traditionally, there are some physical-based models, numerical techniques, and recently the combination of these models, I mean that black box and white box, that is called gray boxes. And in these methods, actually the authors emphasize that these models are a better match to, for example, to simulate better and more realistic rather than only, for example, physical based or only data-driven methods. What do you think of this type of methods? Have you already, for example, tried with these types of models or not?
A good question. Just a quick comment. I think today's presentation is more about data models and how we do the data analytic. And I agree. I think that's an opportunity also, thinking about how we use the sensor metadata, to support the model creation using tools like Energy Plus. Also used to calibrate those physics based models. And it's also a technique combine data and models. I think one of our previous research look at how to use the inverse modeling technique. So I think it's all these different opportunities. Again, depends on what data you have and what kind of applications you are interested. So definitely, thinking about data can be used in multiple ways, very flexible ways.
You mean that from one application to another application, it would vary? For example, in one application, we could only use the data-driven methods, machine learning methods, and for another application, gray box methods would be better match?
I think so. Yeah, obviously, depends on the specific application. You have to do some, assessment. And the reality is, you probably get access to different types of data, different resolution, different quality, So that's what you have. And then when you're talking about physics model, it also depends on the level of detail, how much you want to spend time and effort to create a model, So quite often you combine both data and models together, to address your application needs.
Thank you very much.
Okay, it's probably a good time to end our webinar. It's 15 after past the hour, and I want to thank our speakers again, Tianzhen, Na, and Han, for a very interesting presentation and for all the questions. The topic is definitely timely, where we had quite a few questions there and people interested in learning more about your work. So thanks again, and thanks everyone for attending.
Thanks, Kamal, and thanks the BD subcommittee for organizing this. And thanks for audience. Thank you so much. Bye-bye.
Thanks, bye now.
Thanks,
Bye-bye.
everyone. Bye.
Goodbye. Bye.